Hey guys, here we are again. Today we're really going to start getting deep into proving. We've talked a lot about logic this chapter, but we really need to start getting into proving geometric topics and how do you prove. So this section right here will kind of show you how to write up a formal geometric proof. But we're going to do it with something simple, just with line segments, so that way try to keep the topic fairly simple, so that way you can kind of get a general idea of how proofs work. So now you want to keep in mind your logic that we've been working on. You want to keep in mind how the logic process works. Everything we do for a reason. There's a reason for every step. One thing leads to another. It's like a chain reaction. So if you'll keep in mind that theorems are like chain reactions, then you shouldn't have any problem. All right, so let's write some notes. Hopefully you've got your notes there, and I've got my first page just taped down right here to my binder. So if you haven't done that yet, you might want to do that. It required me to cut off the borders there. So the first thing is a theorem. A theorem is a true statement that follows as a result of other true statements and can be proved. A true statement that follows as a result of other true statements and can be proved. So we're going to be proven. Every time you see the word theorem, from now on, you're going to know that there's probably a proof in your near future. All right, because we're going to do that a lot. So I'm going to highlight theorem. All right, and I don't want you to forget to go ahead and put today's date at the top of your paper, so that way we have that. All right, the next thing is a two-column proof. Pretty much everything that we do is going to be in two-column proof format. There is other formats as well, but this is probably one of the most geometric, most popular one that we use. A two-column proof has numbered statements, so numbered meaning 1, 2, 3, 4, and reasons that show logical order of an argument. Alright, so we did some proofs the other day with the algebra statements, where we did one column we had the algebra going down, and the other column we had the reasoning. So that's a two-column proof. Alright, your very first theorem. Theorems need to be proven. It's not like a postulate. Postulates we can assume to be true, but theorems have to be proven. The first one we're going to prove is the property of segment congruence. Alright, which says it is for any segment AB, comma, we know that a line segment AB is congruent to line segment AB. So I'm going to draw a picture here of line segment PQ and line segment XY. And you're always given information in proofs, so you'll love your given information because that helps get you started. The given information is, I'm going to tell you for sure that PQ is definitely congruent to XY. And what we're going to prove is that XY is congruent to PQ. Doesn't that sound silly? Seems a little ridiculous, but basically that's what the reflexive property is. It's proving that it's congruent to itself. Alright, so you always start, number one, you always start with the given. So we'll say in this line segment PQ is congruent to line segment XY. All right, from that, and we've talked about this before, from that, since we know they're congruent, then we know their measures are equal. So that's going to be the following statement. PQ must equal XY. All right, because that's just the definition of what congruence is. You're going to use that a lot this semester. Okay, going from a congruent statement to an equal statement. We just call that definition of congruence. Step 3, XY, then we know equals PQ. And we got that kind of from our algebra that we did the other day. All right, our algebra, one of our algebra properties, in specific, the symmetric property of equality that we talked about the other day, says that we can flip-flop our equal sign, and that's okay. Well, if XY is equal to PQ, then I have proven what I set out to prove right down here. XY is congruent, line segment XY is congruent to line segment PQ. And the reasoning there is, again, definition of congruence. And I'm going to put my little therefore symbol right out there to show that I'm done. So I want you to notice that your given statement is always at the top and your proved statement is always at the bottom. All right? I can think of 100% of my students that should be able to get the first and the last statement of every proof. All right? Super, super easy. All right, so the next one is the transitive property. We know what the transitive property is for numbers. If A equals B, then B equals C. If A equals B and B equals C, then A equals C. Well, it's true for segments also. So it says for any segments AB, CD, and EF, then if AB, I'm going to run out of room here a little, if AB is congruent to CD, if AB is congruent to CD, and CD, line segment CD, is congruent to line segment EF, comma, then line segment AB must be congruent to line segment EF. That's just the way it works. All right, if A equals B and B equals C, then A equals C. All right, the proof for that is actually going to be in your homework. Proof right there is in homework assignment. So we're not going to prove that now. All right, the next thing, the paragraph proof. All right, I'm going to have to write the paragraph proof down here a little lower. The paragraph proof is a proof written in paragraph form. A proof written in paragraph form. All right, so basically what happens is instead of you organizing it like this, nice and neat in a little chart, you basically just tell me a story of how do you get from point A to point B. All right, and so we'll see some of those here and there as we go. I can give you kind of an example of how this one would go. It looks like this. Maybe if you were just going to write this out in a paragraph, you'd say, when given line segment PQ is congruent to line segment XY, we know that PQ is equal to XY. Because, you have a lot of becauses in paragraph proofs. Because of the definition of congruence. So then you'd say, then XY equals PQ. So you can see that statement right here. XY equals PQ. Because of the symmetric property. Because of the symmetric property of equality. So it follows that XY is congruent to PQ because of definition of congruence. Because of definition of congruence. Sorry about that. That was a mess. You can see how it just takes a lot more words to write a paragraph proof out, but you basically say the exact same thing you said up here, you just write it as paragraph. Alright, pretty simple. Alright, we're going to try a couple of these just to kind of show you how geometric proof might go. I'm going to zoom in on these a little bit, see if we can see them better. Alright, the first one is HI is equal to 8. So I'm going to put that on my picture. You should always put your numbers on your picture. Then it says IJ is equal to 8. And then we know that IJ is congruent to JH. So I'm going to put little lines like that so that I remember those two sides are congruent. The goal here is to prove that HI, line segment HI, is congruent to line segment, HI is up here. HI is congruent to JH. So we're going to prove that this 8 and that line segment right here are congruent. Now you can see over here that the statements have already been filled in for you, so we're just going to give the reasons. So that's kind of nice. So the first two statements you can see, of course, are in the given information. And they should be, because our first statements are always given. A lot of times we don't write it twice, we just cram all the given into one statement and then we just write given. So you don't really need to put everything in a separate statement, you can just put it all as number 1. But then we got number 3 here, HI is equal to IJ. So that's clearly true, HI is equal to IJ. So that's basically your substitution property. Substitution. Because if HI equals 8 and IJ equals 8, then HI must equal IJ. You can use substitution. Some people might like to call that transitive, and that's kind of okay too. Every once in a while we can substitute transitive property in there instead, but we're going to call this one substitution property. Okay, then from there we go down here, and most of you can guess if it goes from the inequality statement HI equals IJ and it goes straight to the congruent statement. All you have is definition of congruence right there. Then it's going to flip-flop. Check that out. We're flip-flopping that around here. We've got the IJ here, and then we put, looks like we substituted in, instead, we know that IJ is equal or congruent to JH. Oh my goodness. I'm sorry, I didn't notice it. Check this out. It's right here. It's a given statement. Normally, we do not put our given statements on step 5. It would have gone up here, but this is a textbook problem and one that I didn't write, so we'll just say that's given information. Alright, and so I hope you can see where this is going. If HI is congruent to IJ and IJ is congruent to line segment JH, then by transitive, these two guys must be congruent, and that's what it says right here. So therefore, HI is congruent to JH by the transitive property. And there's how you go from point A to point B. Alright, if you want to see that one again, of course you can rewind it, but we're going to move on. Alright, this one says given AL is equal to SK. So that's my first statement. I'm going to just go ahead and write given in that spot. We are going to prove that AS is equal to LK. We're going to try to prove that AS right here is equal to LK, knowing that AL is equal to SK. So I'm going to put little marks on my paper right there just to show that they are congruent. Alright, according to this, step 1, LS is equal to LS. Well, that's your reflexive property. Alright, we've talked about that one before. Anything we've talked about in the past is fair game. So as long as we've discussed it, I don't care what chapter it came from, you can write it down. Alright, the next thing it says, looks like we got AL plus LS. equals SK plus LS. So it looks like we took these LS's and we just added the same thing to both sides of the equation. Alright, we've got LS and LS on both sides. So that's the addition property of equality. The addition property of equality. Alright, so we're looking here, AL plus LS, that's the same as before, equals AS. Well, let's look at that. AL plus LS, that equals the entire segment. So that looks like a little segment addition property. Segment addition postulate. Sorry, that's the postulate that we talked about the other day. Segment addition postulate. It was on your Chapter 1 test. Alright, number 5. SK plus LS is equal to the entire segment LK. That's again segment addition postulate. Alright, so the grand finale then, we must be there. Therefore, AS must be equal to LK, and we're going to call that just a little substitution. If you look back up here, how do we know that these two are equal? Well, AL plus LS is right here. SK plus LS is right here. We already said these two statements are equal. So if these two statements are equal, then these have to be equal, and that's what we put down here. If you want, you can call that transitive property. A equals B and B equals C, then A must equal C. So to me it kind of looks like the transitive property. I do like substitution better in this case, because basically what we're doing is we're taking AL plus LS, we're taking this AS and substituting it in there. And we're taking SK plus LS is LK, so we take it and substitute it right there. Move it up there. And that's how you get this statement. Alright, now all I need you to do is take the rest of it, and what I want you to do is I want you to cut it out. I mean, in other words, I want you just to cut off the borders, and I want you to tape it one page here, and then one page here, and then I want you to be done. I want you to close your book, and I want you to bring that to class completely undone, because we're going to do that together in class. And you guys have a wonderful day.